Hello and welcome. In this video, we will explore the properties of curves, specifically focusing on how to determine where a function is increasing or decreasing, and how to find and classify its stationary points. These concepts are fundamental in calculus and are a key part of the IB mathematics analysis and approaches higher-level curriculum. By the end of this video, you will be able to define increasing and decreasing functions, use the first derivative to find intervals of increase and decrease, identify and classify stationary points as local maxima, local minima, or stationary points of inflection, and solve IB-style problems involving these concepts. Let's begin with the concept of increasing and decreasing functions. Intuitively, a function is increasing if its graph goes up as you move from left to right, and decreasing if its graph goes down. More formally, for an interval S in the domain of a function f of x, we say f of x is increasing on S, if for any 2 points a and b in S, where a is less than b, the function value at a is less than or equal to the function value at b. Conversely, f of x is decreasing on S if for any 2 points a and b in S, where a is less than b, the function value at a is greater than or equal to the function value at b. Let's look at a classic example, the parabola y equals x squared. As you can see from the graph, as we move from left to right, the curve goes down until it reaches the origin, and then it goes up. This means the function is decreasing on the interval from negative infinity to 0, and increasing on the interval from 0 to positive infinity. A common point of confusion is the vertex at x equals 0. Is the function increasing or decreasing at this single point? The answer is that the concepts of increasing and decreasing apply to intervals, not to individual points. So, we say the function is decreasing on the interval x is less than or equal to 0, and increasing on the interval x is greater than or equal to 0. While we can determine intervals of increase and decrease from a graph, a more rigorous and powerful method involves calculus. The key is the first derivative. Recall that the derivative, f prime of x, represents the gradient of the tangent line to the curve y equals f of x at any point x. If a function is increasing, its tangent lines will have a positive slope. If it's decreasing, its tangent lines will have a negative slope. This leads to a crucial test. A function f of x is increasing on an interval S if its derivative f prime of x is greater than or equal to 0 for all x in S. Similarly, f of x is decreasing on S if its derivative f prime of x is less than or equal to 0 for all x in S. This test is the foundation for finding these intervals algebraically. Let's see how it works with an example. Let's find the intervals where the function f of x equals x cubed minus 3x plus 4 is increasing or decreasing. Our first step is to find the derivative, f prime of x. Using the power rule, the derivative of x cubed is 3x squared, and the derivative of negative 3x is negative 3. The derivative of the constant 4 is 0. Easy. Next, we need to find the critical points, which are the x values where the derivative is 0. We set f prime of x equal to 0 and solve for x. Factoring out a 3 gives us 3 times the quantity x squared minus 1. This is a difference of squares, which factors into 3 times x minus 1 times x plus 1. Setting this to 0 gives us x equals 1 and x equals negative 1. These critical points divide the number line into 3 intervals: x less than negative 1, x between negative 1, and x greater than 1. We will test a value from each interval in the derivative to determine its sign. For the interval x less than negative 1, Let's test x equals -2. F prime of -2 is 3 times -2 squared minus 3, which is 9. Since 9 is positive, the function is increasing on this interval. For the interval between -1 and 1, let's test x equals 0. F prime of 0 is 3 times 0 squared minus 3, which is -3. Since -3 is negative, the function is decreasing on this interval. Finally, for the interval x greater than 1, let's test x equals 2. F prime of 2 is 3 times 2 squared minus 3, which is 9. Since 9 is positive, the function is increasing on this interval. We can now complete our sign diagram. It shows a plus sign, then a minus sign, then a plus sign. This tells us that f of x is increasing for x less than or equal to -1, decreasing for x between -1 and 1, and increasing for x greater than or equal to 1. Now let's move on to stationary points. A stationary point is a point on a curve where the gradient is 0. This means that at a stationary point, the tangent line to the curve is horizontal. To find these points, we simply set the first derivative equal to 0 and solve for x. There are 3 types of stationary points we need to be able to classify. First, a local maximum. This is a point that is higher than all other points in its immediate vicinity. The function increases before it and decreases after it. Second, a local minimum. This is a point that is lower than all other points in its immediate vicinity. The function decreases before it and increases after it. Third, a stationary point of inflection. This is a point where the curve changes its curvature, but the gradient is still 0. The function continues to increase or decrease on both sides of the point. A classic example is the origin on the curve y equals x cubed. The sign diagram of the first derivative is the perfect tool for classifying these points. Let's see how. Let's classify the stationary points of the function f of x equals x cubed minus 3x squared minus 9x plus 5. First, we find the derivative, f prime of x, which is 3x squared minus 6x minus 9. Then we find the critical points by setting the derivative to 0. Factoring gives us 3 times x minus 3 times x plus 1 equals 0. So our critical points are x equals 3 and x equals -1. Next, we create a sign diagram for f prime of x. We test values in the intervals around our critical points. For x less than -1, f prime is positive. For x between -1 and 3, f prime is negative. For x greater than 3, f prime is positive. Now we can classify the points. At x equals -1, the derivative changes from positive to negative. This indicates a local maximum. At x equals 3, the derivative changes from negative to positive. This indicates a local minimum. Finally, we find the y-coordinates of these points by substituting the x values back into the original function. F of -1 is 10, so the local maximum is at -1, 10. F of 3 is -22, so the local minimum is at 3, -22. Let's consider a more complex example involving a rational function. We'll find the intervals of increase and decrease for f of x equals the quantity 2x minus 3, divided by the quantity x squared plus 2x minus 3. First, we need to find the derivative using the quotient rule. The quotient rule states that the derivative of u over v is v times u prime minus u times v prime, all over v squared. Applying the rule, we get 2 times the quantity x squared plus 2x minus 3, minus the quantity 2x minus 3 times the quantity 2x plus 2, all over the denominator squared. After expanding and simplifying the numerator, we arrive at -2x squared plus 6x. We can factor the numerator to -2x times the quantity x minus 3. The denominator can be factored to x minus 1 times x plus 3 and then squared. This gives us our derivative in a factored form, which is essential for the sign diagram. Now, we find the critical points by setting the numerator to 0, which gives x equals 0 and x equals 3. We also need to consider the points where the function is undefined, which are the vertical asymptotes at x equals 1 and x equals -3. These 4 points divide our number line. We test a value in each of the 5 intervals. The denominator is always positive because it's a square, So we only need to check the sign of the numerator, negative 2x times x minus 3. This gives us a sign diagram of minus, minus, plus, plus, minus. From the sign diagram, we can conclude that the function is increasing on the intervals from 0 to 1 and from 1 to 3. It is decreasing on the intervals from negative infinity to negative 3, from negative 3 to 0, and from 3 to positive infinity. Let's work through another example, this time involving an exponential function. We'll find the exact position and nature of the stationary point of y equals the quantity x minus 2 times e to the power of negative x. We need to find the derivative di dx using the product rule. The product rule states that the derivative of u times v is u prime v plus uv prime. Applying the rule, we get 1 times e to the negative x, plus the quantity x minus 2 times negative e to the negative x. We can factor out e to the negative x, which gives us e to the negative x times the quantity 1 minus x plus 2. This simplifies to e to the negative x times the quantity 3 minus x. To find the stationary point, we set the derivative to 0. Since e to the negative x is never 0, we only need to solve 3 minus x equals 0, which gives us x equals 3. Now we create a sign diagram for dA dx. We test a value less than 3, like x equals 2. dA dx is positive. We test a value greater than 3, like x equals 4. dA dx is negative. The derivative changes from positive to negative, indicating a local maximum. Finally, we find the y-coordinate by substituting x equals 3 into the original function. Y equals 3 minus 2 times e to the negative 3, which is 1 over e cubed. So, the exact position of the local maximum is at the point 3, 1 over e cubed. Sometimes, we are asked to find the greatest and least values of a function on a closed interval. This is a slightly different problem. The greatest and least values, also known as the global maximum and global minimum, can occur at two types of points, either at a local maximum or minimum within the interval, or at one of the endpoints of the interval, as. Therefore, our strategy is to find all these candidate points, calculate the function's value at each of them, and then compare the results. Let's find the greatest and least values of y equals x cubed minus 6x squared plus 5 on the interval from negative 2 to 5. First, we find the derivative, which is 3x squared minus 12x. Setting it to 0 gives us 3x times x minus 4 equals 0, so the critical points are x equals 0 and x equals 4. Both of these points lie within our interval. Next, we evaluate the function at the critical points and the endpoints of the interval. At x equals 0, y is 5. At x equals 4, y is negative 27. At the left endpoint, x equals negative 2. Y is negative 27, and at the right endpoint, x equals 5, y is negative 20. Comparing these four values, the greatest value is 5, which occurs at x equals 0. The least value is negative 7, which occurs at both x equals 4 and x equals negative 2. Let's tackle a more abstract problem, which is common in IB exams. We are given that the function f of x equals 2x cubed plus x squared minus 24x plus 1 has a local maximum at x equals negative 4. We need to find the value of the constant a and the coordinates of the local maximum. The key information here is that there's a local maximum at x equals negative 4. This tells us two things. First, since it's a stationary point, the derivative at x equals negative 4 must be 0. Second, since it's a local maximum, the derivative must change from positive to negative at x equals negative 4. Let's start with the first condition. We find the derivative, f prime of x, which is 6x squared plus 2ax minus 24. We know that f prime of negative 4 must be 0. Substituting x equals negative 4 into the derivative gives us 6 times 16, plus 2a times negative 4 minus 4, which equals 0. This simplifies to 96 minus 8a minus 4 equals 0, or 72 minus 8a equals 0. Solving for a, we find that a equals 9. Now that we have the value of a, we can write the full derivative. F prime of x equals 6x squared plus 18x minus 24. We can factor this to 6 times x plus 4 times x minus 1. The critical points are x equals negative 4 and x equals 1. Let's check the sign diagram. For x less than -4, f prime is positive. For x between -4 and 1, f prime is negative. For x greater than 1, f prime is positive. This confirms that at x equals -4, the derivative changes from positive to negative, which is indeed a local maximum. At x equals 1, it's a local minimum. Finally, we find the coordinates of the local maximum. We substitute x equals -4 into the original function, now with a equals 9. F of -4 equals 2 times -4, plus 9 times 10, plus 96, plus 1. This calculates to seen. So the local maximum is at the point -4, 17. Let's conclude with a final challenging example. We are given a cubic polynomial p of x equals x cubed plus bx squared plus cx plus d. We are told it touches the line y equals 9x plus 2 at the point 0, 2, and has a stationary point at -1, -7. Our goal is to find the polynomial p of x. This problem gives us 4 pieces of information, which is perfect since we have 4 unknown coefficients, a, b, c, and d. We will translate each piece of information into an equation. First, the point 0, 0, 2 is on the curve. So, p of 0 must equal 2. Substituting x equals 0 into the polynomial gives d equals 2. Second, the curve touches the line at this point, which means they have the same gradient. The gradient of the line is 9. The gradient of the curve is p prime of x. So, p prime of 0 must equal 9. The derivative is 3x squared plus 2bx plus c. Substituting x equals 0 gives c equals 9. Now for the second piece of information. The point -1, -7 is on the curve. So p of -1 must equal -7. Substituting x equals -1 gives -a plus b minus c plus d equals -7. Since we know c is 9 and d is 2, this simplifies to -a plus b equals 0 or a equals b. Finally, it's a stationary point, so the derivative at x equals -1 must be 0. P prime of -1 equals 0. Substituting x equals -1 into the derivative gives 3a minus 2b plus c equals 0. We know c is 9, so 3a minus 2b plus 9 equals 0. We now have a system of 2 equations with 2 unknowns. A equals b, and 3a minus 2b equals -9. Substituting a for b in the second equation gives 3a minus 2a equals -9, so a equals -9. Since a equals b, b is also -9. We have found all 4 coefficients. A is -9, b is -9, c is 9, and d is 2. Therefore, the polynomial is p of x equals -9x cubed minus 9x squared plus 9x plus 2. Let's quickly recap what we've learned. We've seen that the sign of the first derivative, f prime of x, tells us whether a function f of x is increasing or decreasing. We've also learned how to find stationary points by setting the derivative to 0 and how to classify them as local maxima, local minima, or stationary points of inflection using a sign diagram. These techniques are powerful tools for analyzing the behavior of functions and are essential for success in IB mathematics. Now, to solidify your understanding, here are 5 practice questions in the style of the IB exam. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Find the intervals where f of x equals x cubed minus 6x squared plus 9x plus 2 is increasing or decreasing. Question 2. Find and classify all stationary points of f of x equals x to the power of 4 minus 2x squared. Question 3. Find the greatest and least values of f of x equals x plus 16 over x on the interval from 1 to 4. Question 4. The function f of x equals x cubed plus x plus b has a stationary point at -2, 3. Find the values of a and b. And question 5. Show that y equals 4e to the negative x times sin x has a local maximum when x equals pi over 4. Welcome back. Let's go through the solutions. For question 1, we find the derivative, 3x squared minus 12x plus 9, and set it to 0. This gives critical points at x equals 1 and x equals 3. The sign diagram shows the function is increasing for x less than or equal to 1 and x greater than or equal to 3, and decreasing for x between 1 and 3. For question 2, the derivative is 4x cubed minus 4x, which factors to 4x times x minus 1 times x plus 1. The critical points are x equals -1, 0, and 1. The sign diagram shows a local minimum at x equals -1, a local maximum at x equals 0, and another local minimum at x equals 1. The corresponding points are -1, -1, 0, 0, and 1, -1. For question 3, we find the derivative of x plus 16 over x, which is 1 minus 16 over x squared. Setting it to 0 gives x equals 4. We evaluate the function at this critical point and the endpoints of the interval. F of 1 is 17, f of 4 is 8, and f of 4 is also 8. The greatest value is 17 and the least value is 8. For question 4, the derivative is 3x squared plus a. Since there's a stationary point at x equals -2, f prime of -2 is 0, which gives a equals -12. The point -2, 3 is on the curve, so f of -2 is 3. Substituting a equals -12 gives b equals -13. For question 5, we use the product rule to find the derivative, which is 4e to the negative x times the quantity cos x minus sin x. Setting this to 0 gives cos x equals sin x or tan x equals 1. The solution in the first quadrant is x equals p psi over 4. The sign diagram shows the derivative changes from positive to negative at this point, confirming it's a local maximum. That concludes our exploration of increasing and decreasing functions and stationary points. You are now equipped with the calculus tools to analyze the behavior of a wide range of functions. Remember, practice is key to mastering these concepts. Continue working through problems from your textbook and past papers. Thank you for watching.